Okay, this is Unit 2, Atomic Theory, Lesson 2. At the end of the last lesson, the lesson stopped, I guess, before it was supposed to, and we did not cover wave mechanical cloud model, which is our modern present-day model. So we're going to pick up with that, and then we are going to review the significant contributions that were made by various scientists regarding atomic theory and who have brought us to where we are today. So in the wave mechanical cloud model, which is our present-day model, this was developed after the famous discovery that energy is made up of both waves and particles. So what's the same? Well, as the previous theory, we still have the same dense positively charged nucleus. So that hasn't changed. However, electrons now have distinct amounts of energy and move in areas called orbitals. And that energy that we're talking about is quanta. Another way that we can say this is regions around the nucleus where electrons are most likely to be found. The Regents exam loves to use the words probable location. Many scientists have contributed to this modern theory. And it's different from the Bohr diagram because the electrons are no longer in fixed paths, but they are based on probability within the orbital. So that was the last one that you missed. So what we're going to do now is basically review. How I've seen this asked on the Regents exam is in a couple of ways. Sometimes they refer to chronological order. What is the chronological order of different contributions? And they may give names in a multiple choice question. Sometimes they'll specifically ask about a particular experiment. They love to compare J.J. Thompson and Ernest Rutherford. They often refer to Niels Bohr's model as the planetary model. So we're going to go through some of these now. One thing I can tell you that you definitely can be sure of is that I've never seen them test you on dates, but we will put the dates. So the atomic model, let's start in 1803, and that started with Dalton. So this is a recap of what we've done, and the name of the model is the cannonball model. Remember, he said that atoms were indestructible, and he called them atomos. Well, no, and he called them atoms, from the Greek word atomos. What did he conclude? That the atom was a solid sphere, and it had uniform density. Okay. Next was 1897, J.J. Thompson. And he had the plum pudding model. And conclusions from that were that there were small, negatively charged electrons embedded within the atom. And the positive charge was dispersed evenly. Similar to, I'm going to put rice pudding because I think you're more familiar with that than plum pudding with raisins. So if we were to draw a picture of that, here's our atom. This is all positive. All of this is positive. And then your electrons were embedded in it. Let's see a quick video clip of the cathode ray tube, and this is what led to J.J. Thompson discovering the electron.
To demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream. Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
So that's how J.J. Thompson discovered the electron, was playing around with the cathode ray tube and seeing what happened to this beam of light when he had a magnet near it. And he noticed that the beam would go one way or the other depending on which way he turned the magnet. And he knew that the magnet had a positive end and a negative end, so therefore opposites attract and like charges repel. So whenever he would hold up the negative end of the magnet to the cathode ray, it would deflect the other way, and that's how he discovered the negative charge. So let's move on now to Ernest Rutherford, who in 1909, Rutherford, and he's famous for well, the name of his experiment is the nuclear model, and this is the gold foil experiment. I've never heard the regents refer to it as the nuclear model. They've always referred to it as the gold foil experiment. And as a result of the experiment, he determined that the atom is made up of mostly empty space. So the atom is mostly empty space. And that the atom has a dense positive charged center. And this is what we now call the nucleus. And he said that electrons were found outside the nucleus. And now we will look at his experiment.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
So the positive particles were alpha particles, which are really a helium nucleus, and that's what they projected toward or through the gold foil. And the reason that most of them went through was because the atom was made up of mostly empty space. The few that were deflected because they had come in contact with the nucleus, which was positively charged. Again, like charges repel. Moving on, after Rutherford, we had Niels Bohr in 1913. And he's known for his planetary model. You will sometimes hear it referred to as the Bohr model after him. And he said that electrons were found in well-defined orbits. Or paths outside the nucleus, much in the same how planets orbit the sun. He also said that electrons in each orbit have a definite amount of energy. I just abbreviated amount. He also said that if electrons become excited, they can jump, so to speak. to an orbit further from the nucleus. We can't do that with planets. And we're going to learn this in a little bit more detail, but when this happens, when they're jumping basically from a low level to a higher level, they absorb energy. So in order to make that quantum jump, they have to absorb energy. When excited electrons lose energy, they give off light. So here we're going from a high level to a low level. Energy is released. In the form of light. And we're going to talk more about that, but I just want to introduce that now. And let's talk about our last atomic model now. And this was many scientists, but there was one that was given a lot of credit, and you don't have to know his name, but it was Schroedinger. You'll talk more about him in physics. I have a little joke for you at the end of this. Make up for my wayward ways last time. And that is our wave mechanical or cloud model. So, what were the conclusions from this? Basically the same as the planetary model, except, and this is the important part, no definite orbits. Electrons are found in orbitals. And their location is not well defined because they're constantly moving. It allows us to predict the probable location of an electron or electrons. Okay. And that's it for tonight.
Imagine
Imagine that you take a cat and put it in a box. Also in the box, you put a small lump of radioactive material and a vial of poison gas. There is an exactly 50-50 chance that an atom in the radioactive lump will decay and emit an electron. If it does decay, then it releases the gas and kills the cat. If it doesn't, the cat lives. 50-50. The point is, there's a rather extraordinary consequence. Until you do open the box, the cat exists in an indeterminate state. The possibility that it is alive and the possibility that it is dead are two different waveforms superimposed on each other inside the box. Schrödinger put forward this idea to show the absurdity of quantum theory.
So, I will leave you with that to ponder. See you Monday.